Okay, so we'll start the session. So here also, if you are having any sort of a question or related stuff, please use the chat box. Then I can reach you guys. Okay. So today we are in the physics session. We are going to discuss about the solids, liquids, and gases related stuff, which means the unit 5, right? So here I'm going to like within 1 hour or 1.5, I'm going to refresh or remind all the revise all the important stuff that you're going to get here. Okay. So here the first thing that you need to know. So here when it comes to solids, we need to know what is meant by the density, right? So no need of remembering the definition, but it's okay if you can remember the definition. So here the density measures how tightly matter is packed. It is the mass of a substance per unit of its volume, right? So that is the main definition that you need to remember. Density is the mass of a substance per unit of its volume, right? Per unit, which means a single part, right? Per unit. And equation is this thing. And here, instead of simple D, normally the standard symbol is rho, right? Symbol is rho for density. Some cases you can use simple D as well, but it's better to use this symbol rho here. So density equals mass over volume. So if you apply the standard units, then you can see it will be kilograms per cubic meter, right? Kilograms per cubic meter. And in some cases, it will be like grams per cubic centimeter as well, right? Grams per cubic centimeter. It depends actually. So as I mentioned yesterday as well, so please pay attention to the unit that they are asking in the question paper, and according to that you need to change the units and go for the unit conversion and so on, right? So then measuring the density of different sort of substances. So if we consider the first one for the liquid measurement, right? So first you are going to place the measuring cylinder on a balance like this, and you need to tear it uh, to avoid the zero error, which means so here it will be measuring the mass of the measuring cylinder as well, right? So we don't need to add that error point. So therefore, we need to omit the mass of the measuring cylinder. So therefore, we need to tear the balance. So there's a special key in order to make the reading zero. So normally that is given in capital T. There's a button, special button, right? So when you press this button, what happens is that the reading which is in that specific moment, right? So here we have placed the measuring cylinder on the pan, and it is giving a value. So once after that, we are tapping this tear button or pushing that button. Then what will happen is that the reading will become zero, right? So which means the mass of the measuring cylinder is now neglected, right? It's omitted. Or otherwise, then you need to do, or you need to go for another step to remove the mass as well, right? So once it is become zero, then what you can do is that you can pour the liquid into the measuring cylinder, and then it will be giving you the direct mass of the volume, right? It will be giving the direct mass of the volume. The reason is like we remove the mass of measuring cylinder. And also when you are pouring the solution or the liquid into the measuring cylinder, you need to have the measurement in your eye level in order to avoid the parallax error, right? In order to avoid the parallax error, you need to get the read in the volume value uh, in the eye level. Afterwards, you can use the calculation, and you can calculate the what you call that density value. And when it comes to regular shaped objects, so here the regular shaped object will be placed on the balance on the pan first. And first you are going to measure the mass value. Then since it is a regular shaped object, we can measure the volume as well. So if you know the width, length, and the height, then you can get the volume value. So you know the you know the mass value, you know the volume, then you can go for the density measurement, right? And this is the uh, important part. This is the irregular shaped object or irregular object. So first we are going to place the object on the pan, and we will be getting the mass value. And then we will be using the displacement can, or you can use or the term Eureka can, right? Both are correct. Eureka can, or this is going to be the displacement can, right? So in this displacement can, remember the water levels must be up to the spilling point. So those are some important points that I'm emphasizing. So this is the cross-sectional diagram of the can. And remember the water level, if you use it at this level, it is wrong, right? The reason the water might spill or not, we cannot guarantee. So therefore, the correct method is you need to fill the water up to this level. Then once you are submerging this object, then what will happen? The water, the excess water will be spilling like that, right? So remember that point. So we are using the displacement can. So the volume of water displaced will be equal to the volume of solid. So in this case, you can see it is partially submerged. So in this case, it will give you only the volume of the part where the solid is partially submerged. So therefore, it is a must, right? So that you need to somehow you need to fully submerge this object in water, right? Otherwise, you cannot get the full volume. So keep that in mind, right? So volume of the water displaced will be equal to the volume of the solid. So we know the mass and the volume. So then we can do the calculation. And in the classes as well, I have emphasized this thing. So when we are measuring, so the first step would be measuring the mass. Then we are going for the volume. If a student go for the second technique like this, so he is going to measure the volume first and then the mass. So this approach is wrong. The reason is, like, we don't know that whether this object, this irregular shaped object, this substance is going to, like, whether it is going to absorb water or something like that. So if it is absorbing water, then in the second step, we will be measuring a higher mass. So it will be leading to false result. So therefore, this is the correct method. First, you are going to measure the mass, then you are going to measure the volume. So then in the first method, there's no connection between the absorption or anything related to that. So remember that point. There can be some tricky questions like this, whether to comment on whether which student has the correct approach for this practical setup. Okay, so remember this, and I will upload this tut as well, right? So no need of printing. If you need, you can print it, but you can refer it. Okay. Then the pressure of a solid, so it will be equal to P equals F over A. So force over area unit will be pascals. And if we use the standard units here, so it will be newtons divided by square meters. So therefore, it will be Newton per square meter. So which means this will be equal to Pascal as well, right? This will be equal to Pascal as well, right? Then uh, this situation. So there are so many things that we can discuss here, right? So if we use this equation, you can see that if area is constant, then pressure will be directly proportional to force. And the second one, if force is constant, then pressure will be inversely proportional to area, right? So better to remember these two relationships, right? So if area is same and you are experiencing two different forces, then definitely you are having two different pressure values. And in the second case, if the force is constant, if the force is same, but the surface area which is being applied is now different. So which means the pressure will be different. And here it is inversely proportional. So that thing is explained here. So you are having the same force. So in this case, we are using the body weight. So which means we can nearly think that they are equal to each other. And here you can see it is being applied on a single nail on the area. And so here you can see there will be a high pressure exerted. The reason is like if the area goes down, then what will happen according to pressure inversely proportional area. So this goes down. So therefore pressure goes up, right? And here now you have a huge area, large area, right? So therefore what will happen? Now the area is higher, so therefore pressure inversely proportional to area. Area is higher, so therefore pressure will decrease, right? A simple connection. Remember those points. And the next one, pressure generated due to a liquid. So in the theory classes, I explain how we can get this equation and all the stuff. But for you guys, there's no need of memorizing or memorizing how to get that equation. But you need to remember the pressure equation. So the pressure equation is H rho G. I don't know why there are two times written here, right? So it will be H rho G. So it will be height or depth, right? Height or depth. Most of the cases, it will be depth into density into gravitational field strength, right? So remember depth, right? So which means we are measuring from the liquid surface, right? So if we consider something like this, so this is H1 and this is H2, right? This is H2. And we'll say there's a place at the bottom which is going to be H3, right? So I label this to be A, B, and C. So for PA, I'm considering the depth. So in this case, the depth will be H1, rho G. Rho is the density of this thing, right? Density of this liquid, and we are experiencing the gravitational field strength. So this is the first equation. And if we consider about PB, density at the second position. So now you need to get the total depth, right? Now you need to get the total depth. So it will be H1 plus H2, right? The total depth H1 plus H2. So therefore, it will be H1 plus H2, right? You need to consider the total depth into rho G. Same PC. Now there's another depth point. So it means H1 plus H2 plus H3 rho G, right? And here a point given, deeper in the fluid, more particles above. So therefore the combined weight of the particles increase and therefore the pressure increases, right? Therefore the pressure increases. And in resting fluid, pressure acts equally in all directions, right? Acts equally in all directions and causes a force at right angles to surface, right? So just imagine you are making a hole in the same level here, right? So same distance, the water will spill at the same distance. I think you can remember this thing. So I'm not going to emphasize more on these things. So in previous cases, in previous question papers as well, you got a calculation something like this, right? They have given a bottle, right? And about three different holes like this. And there's water filled up here, A, B, and C. They were asking you to draw the water path, right? So C is having the highest pressure from here. So therefore it will be going a larger distance like this, and B will be might be something like this, and A might be something like this. And also they ask, if you are making another hole here, let's say D, so it is in the same level of C. So therefore, if we consider this distance to be X, then from D hole also, you will be having that water stream, right? That jet stream at the same distance as X. The reason is the pressure at D will be equal to pressure at C. The reason you are experiencing the same height, right? You are having the same height. So remember those points, okay? And remember, if you need to get this sort of a jet stream, so then definitely the topmost part must be open to atmosphere, right? Otherwise, these kind of jet stream won't happen, right? So therefore, remember, there must be atmospheric pressure acting on the wall, on the what do you call this water surface, right? Remember those points. Then about the heat capacity and all the stuff. So remember this equation. So you can get marks for writing this equation, or you can get marks for delta Q equals MC delta theta, right? So both are correct. All the terms have the same meaning. So Q will be the thermal energy change, right? And M is the mass, C is the specific heat capacity, and delta theta is the temperature change, right? Delta theta is the temperature change. And specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Celsius, right? So those are the main 2 points. Specific, you are specifying about the mass there, right? If it is just the heat capacity, then it will be the temperature or the energy required to increase the temperature by 1 Celsius. That's all. But in this case, specific heat capacity means you are focusing on a specific mass value. So that is going to be 1 kilogram. So remember that point. And even in the text, not in the textbook, theory notes, I have given this note. So please refer them. Heating a system increases its internal energy. This energy either makes molecules vibrate faster or breaks the bonds. So if it is breaking bonds, then the state will be changed, right? Whether it means like whether it is going from solids to liquid or from liquids to gases. And here the particles will vibrate faster. So if we consider about that, so particles are now moving at a faster speeds. So speed increases means their kinetic energy will also increase, right? So we discussed about these things. Okay, right. Then you need to remember this graph, right? So normally when we are increasing the temperature of a solid substance, right? If we are increasing the temperature of a substance, then it will go through a series of changes like this, right? So remember this graph consists like only two only two situations, like only two means like only two processes. So one will be the substance being heated, right? The substance heating. That is the first process. And the second one, state change of the state. So the substance heating, it will be demonstrated by a increasing line like this, right? Substance heating, it will be demonstrated like this. And if there's a state change, then it will be a horizontal line like this, right? A state change. So it can be either from solid to liquid, right? But if you are having any sort of a line which is an angled line, then definitely it is for the heating process, right? Remember that. So here in this graph, you can see temperature against time. So which means in this direction, the temperature increases, right? So if we consider here, let's say this is 0 Celsius and time, let's say this is 5, 10, 15, 30. Likewise, it goes. These are just numbers. I need to explain. That's why. And this value to be, let's say, 20. And here it is 80, like that, right? These numbers are just for the explanation process, right? So here 0 means the origin means here you have the solid, right? So once you are increasing the temperature, right? You are providing heat energy. Let's say something like that, right? You are providing heat energy up to 5 minutes, right? So in this process, you can observe that the specific temperature, the temperature of the solid, it increases up to 20, right? It increases up to, sorry, 20. So which means here the solid heating, right? Their temperature increases, right? And it reaches 20. And it reaches 20. So at this point, still you are having the solid. So here also solid at 0 Celsius, but here solid at 20 Celsius, right? So those are two different things. The solid is initially it is at the 0 Celsius level, but at the position B, you have the solid at 20 Celsius, which means the solid is now being heated, right? It's now being heated. Afterwards, still you are increasing the, not increasing the temperature, you are providing that heat energy, right? So here, for 5 minutes, you can observe that here the temperature does not change, right? So for a specific time, you can see the temperature does not change, but in the meantime, you can see the solid slowly starts to start to get liquidized, right? So here the solid will be melting, right? So remember this phase is for the melting, right? Melting. So at C here, you will be having a liquid at 20 Celsius temperature, right? So this process is melting. And the temperature, is it going to change? No. Here you have solid at 20 Celsius, starts melting, and you will be getting a liquid which is also at 20 Celsius, right? Which is also at 20 Celsius. So which means this specific temperature, this 20 temperature will be our melting point for that specific solid, right? It will be the melting point for the specific solid. And again, so still you are providing that same energy. So for the next few 5 minutes, you can see now the liquid is heating, right? So you are having the thermometer, right? You are having the thermometer. So you can clearly observe whether the temperature is going up or it is remaining at the same level, right? So here what will happen? Now the liquid is heating, right? Liquid is heating up to this level. And it reaches point D. So now you are having a liquid at 80 Celsius. You are having a liquid at 80 Celsius. And at that specific moment, so still you are providing energy. So now what will happen? The liquid starts to go to the gas phase, right? It will start to, starts going for the gas phase. So in this specific section, the temperature remains constant. The temperature remains constant, right? Again, in the thermometer, you cannot observe any sort of a increasement in the temperature value, right? So at E, what you can find, it is the now gas, right? Gas at 80 Celsius. And from there onwards, it is just the gas being heated, right? So here, this specific thing, liquid turn into gas, right? So it will be the process called boiling or evaporation, right? So therefore, this point refers us to the boiling point of this specific substance, right? So there were several questions relating to this graph, right? So better to go through this graph uh, again, right? So here it says the horizontal lines, right? Horizontal lines gives us the change of state, right? Horizontal lines gives us the change of state. So which means temperature holds because all incoming energy spent in breaking the intermolecular forces, right? So remember these points. This is a pretty much a good question theory part, okay? Making හොඳ question එකක් අහන්න පුළුවන්. There can be some tricky questions, right? There were so many questions. Please go through the past paper question tutorials, okay? Then you need to know the difference between the evaporation and the boiling, right? So just remember the diagrams, then it will be easier for you to remember. So in the evaporation, right, it will be happening only at the surface, not the inner molecules. But when it comes to boiling, it will be happening throughout the liquid, right? Which means even the inner molecules can be boiled, right? And they can be exiting from the surface. And temperature, it can be the evaporation can occur at any given temperature, right? It's actually uh, a spontaneous reaction, which means there's no need of providing energy also, right? But for the boiling, it occurs at a fixed temperature, which is known as the boiling point, right? A fixed temperature known as the boiling point. And most of the times for the boiling, most of the times in 99%, we need to provide energy in order to occur boiling, right? And mechanism, the highest energy molecules escape, leaving behind the lower average kinetic energy. Bulk energy input forces a total state change, right? Uh, the third point is no need, but just remember, right? The first 2 points, like just imagine in case like in the exam they ask two different, what are the two differences between boiling and evaporation, then you can use the first two points to build up your answer, right? Then the cooling effect, because of evaporation steals the highest energy particles, the remaining liquid is physically cooler. Okay. Then we discussed about the states of matter. So there are mainly three states of matter, but there's a fourth state of matter as well. But for your syllabus, it is not being discussed. Okay. It is known as plasma. Don't write it for the exam. You will lose marks. Okay. So solids, liquids, gases. So particle arrangement, close together, regular pattern. These are the key words that you need to mention, right? Random arrangement, close together. And here far apart, random arrangement. And for the movement, vibration, move around each other, move quickly in all directions. That is the main point, right? In all directions, there are movement. For example, if we consider this gas particle can be moving in this direction, and this can be here, and this can be here. This can be in this direction, and this can be in this direction. Likewise, there's no specific direction of movement. They will be moving here and there as they wish. Okay. And the intermolecular forces, about the intermolecular forces. So for the solids, you have the strong attraction forces, and for the liquids, you have weak attraction forces, and gases, they are going to be very weak. That's why the particles are far apart from each other, right? Far apart from each other. And also uh, try to get the idea of complex compressibility as well, right? They might ask compressibility, which means uh, the compressing ability, right? The ability to be compressed. So here you can see there are so many interparticle spaces. So when you apply forces, these particles can be together. So therefore, compressibility of gases will be higher. That is the highest value, right? They will be having the highest compressibility. And for the solids, they will be having the least compressibility, and this will be somewhere a medium value, right? Somewhere a medium value. Okay. Then the kinetic translation. So everything we measure on the outside is just a shadow of particle behavior on the inside. So kinetic translation in the kinetic motion or something like that. So which means like you are going into molecular levels, which means you are dealing with the particles there, right? You are considering the particle movement, right? Molecular particle movements. So macro observation, macro means the big picture, right? Micro means the you are going into molecular levels. So if the temperature rises, so that is the macro observation. That is the big picture that you are going to see. So which means if the temperature rises, the average kinetic energy of the particles increases. So therefore, the particles will be move faster or vibrate faster, right? You need to build up your answer accordingly. Whether it is a gas particle, then you can say gas gas sample, then you can say that the particles are moving faster. But if it is a solid particle, solid sample, you know that solid particles are not moving, they are vibrating with each other, right? Vibrating here and there. So therefore, you need to mention, you need to use the term vibrations, right? You need to use the term vibrations. And it's the pressure exerted in the wall. So the particles are colliding, right? So these are the terms that you need to use when you are writing an answer, right? Particles are colliding with the boundary and change in their momentum. So when there's a change in momentum, what happens, right? So in the first unit, right, we learned that the change in momentum, right, will be equal to the force generated, and it will be mv minus mu over t, and we can write that F equals m within brackets v minus u over t. So this whole thing becomes the acceleration. So therefore, if it will be F equals ma, right? If it will be F equals ma. So which means the momentum change, right? The momentum change will generate a force, right? The momentum change will generate a force. Momentum change will generate a force, right? So that force being exerted on the wall, so it will be existing, it will be emitted, exerted as a pressure, right? The reason we know the pressure equal F over A, right? The pressure equals F over A, right? A substance melts or boils. So if it is melting or boiling, the heat energy breaks intermolecular bonds, right? Rather than speeding up the particles, right? Which means a huge amount of energy being supplied to that system, right? So small amount of energy means like the particles will be moving here and there. But if you provide a huge amount of energy, now the bonds will be broken. Then afterwards, what will happen? The particles will be having their movement, right? Okay. Then the mechanical origin of gas pressure, or simply we can say how the gas pressure is being generated, right? So as I mentioned in the classes, you need to remember those few steps. So those are the same things that they are going to ask, right? Each and every year, like they will be asking what will happen if the temperature increases, what will happen if the temperature decreases for the gas pressure. So you need to mention, you need to dive to the molecular levels and explain it. Okay. So the first one, the step one, they have given gas molecules move rapidly and randomly. So these terms, rapidly and randomly, they are the most important ones, right? Move rapidly and randomly. Step two, they collide with the container wall and rebound. At least the collide part is must, right? At least the collision, right? They are having those collision. That part is a must. Rebound means like bouncing back, something like that, right? In your level, there's no need of knowing those stuff, but just to be like, just keep it as a point, but in the exam don't write it, right? Normally we consider for the ideal collision. Ideal collision means the energy does not waste, right? So these particles are having kinetic energy. So when they collide with the wall, so they can even make some heat energy and also some sort of a sound energy, right? Likewise, there are so many different sort of energy sources. But in this case, in order to explain this scenario, we assume, right? We think that these collisions are ideal, which means none of the energy is going to be wasted. So therefore, incoming energy equals the uh, outgoing energy, which means here you are having, let's say, 100 kilojoules of kinetic energy, then it collides. So therefore, the bouncing particle will also have 100 kilojoules of kinetic energy. So that is the idea of ideal or elastic collisions, right? That is the idea of elastic collisions. So you will learn these things in A levels, but for this level, there's no need of knowing these elastic collisions or something like that. I just mentioned that because like you need to know what is happening here, right? But in the exam, don't write it. Just write they collide and they changes the direction, which means the velocity is being changed. So therefore, momentum changes. So therefore, there will be a force generated. The force is equal to the change in the momentum over the time, right? So remember these things as a story, right? Then it will be easier for you to remember. Gas pressure isn't just weight, it's the collective force of billions of microscopic impacts. Billions of microscopic impacts, right? So each particle collides and generates a pressure. And finally, we are looking at the big picture. So finally, we can see the huge amount of pressure generated uh, in the system. But if we go into the macro level, there will be billions of particles colliding at every millisecond, right? At every millisecond, you are having these types of collisions, billions of collisions, but the final value will be an output of all the billions of impacts. Okay. Then the temperature changes. So remember, in order to convert into Kelvin temperature, Celsius temperature, you need to add 273 and absolute zero, right? The pressure where the particles stop moving, right? And the Kelvin temperature of a gas is directly proportional to the average kinetic energy of its molecules, right? You can write, I'll write the equation as well. So kinetic energy directly proportional to temperature. Just remember the relationship, that's enough, right? So which means if you increase the temperature, the kinetic energy will increase, right? The kinetic energy will increase. And if you decrease the temperature, kinetic energy will decrease. Remember, in these calculations, right? In these calculations, you need to use the temperature in Kelvin, right? That is a must. Remember, no Celsius temperatures, right? Temperature must be in kelvins, right? In kelvins. And also remember, temperature and heat are two different things. Heat is an energy source, right? Heat is an energy source. So heat, this is an energy source, right? So therefore, energy is being measured in joules or kilojoules. And temperature temperature is the measurement of heat, right? We can use the temperature as a measurement of heat. So this is going to be a measurement. This is going to be in Kelvin or Celsius. Most of the cases in chemistry and physics, we are dealing with Kelvin, right? We are dealing with Kelvin, not Celsius, right? So remember those points. Heat is a energy source is an energy source, therefore joules. Temperature is a measurement, so therefore it will be in Kelvin. And always remember, in this type of calculation, we are dealing with Kelvin, right? Always Kelvin, no Celsius temperature. So though the question is given in Celsius, right? Though the question is given in Celsius, then you need to you need to convert it into Kelvin temperature, right? You need to convert it into Kelvin temperature, right? Then temperature and pressure law, the constant volume thing. So here, if the temperature is low, then low thermal energy, slow movement. So therefore, low particle, low pressure, right? Low pressure. And here, if you are dealing with high thermal energy, fast movement of particles, so the collisions are higher, right? Collisions are higher. So therefore, pressure generated will be also higher. So this is the equation. This is given in a different format, but the same idea, you have the same idea here. In the theory classes, we wrote this equation as P1 over P2 equals T1 over T2. This is the equation that we used in the theory classes, right? But same thing, the base of this thing is the pressure directly proportional to temperature, right? Directly proportional to temperature. So always remember, Kelvin temperature is to be used. Okay, Kelvin temperature is to be used. And here the explanation is given. Heat speeds up molecules. Faster molecules collide harder and more frequently with the walls, driving the pressure up. Right? Heat speeds up the molecules, or you can say when the temperature or the heat energy increases, the kinetic energy increases, right? Include all the points when you are explaining an answer. Then there's a small chance of reducing marks, but you can get the full marks there. So write all the things that you know, right? So heat speeds of the molecule, so therefore what will happen, the kinetic energy increases, so therefore molecules will move faster, and the collisions, they get harder collisions and more frequent collisions with the wall, increasing a high or giving us a higher force value. So therefore the pressure will increase. Therefore the pressure increase. So at least include those 5 points. Okay. Then the Boyle's law, pressure and volume. Pressure and volume. So here P1 equal V1, P1 V1 equals P2 V2, right? So the main theory point here is that P inversely proportional to V, and finally we can say PV will be equal to K. So this is the Boyle's law. And this is somewhat extended version where you can compare two different systems. So most of the time we will be using this equation, right? This equation P1 V1 equals P2 V2, and depending on the situation, you can calculate the wanted pressure or the volume, right? So here, when the volume goes down, pressure will go up, right? And yeah, and here I need to right. So actually we have three different laws. So I'll just discuss about this thing. So gases laws related to gases. So the first one we discussed in the theory class, it is Boyle's law. So equation is PV equals K, and the extended version, it is going to be P1 V1 equals P2 V2. So in order to apply this, right, mass and the temperature are constant, right? Temperature must be constant in this situation, right? And the second one, pressure and temperature. So you got the equation. We can write it like this: P over T equals K. So this is the main equation. Then an extended version, P1 over T1 equals P2 over T2, right? So these are the equations that we are going to use for the calculations, right? So here, in order to use this, M and V are constant. Mass and the volume are constant, right? And the main point, temperature must be given in Kelvin, right? So that is the main point, important point. Temperature must be given in Kelvin. And there's a third law as well, right? The connection between volume and temperature. So it will be volume and temperature like this. So afterwards, you can use it. V1 over T1 is going to be equal to V2 over T2, right? So in this case, pressure and mass are constant. So normally remember pressure, mass, temperature, and volume. So these are the factors that we can change for a gas, right? Those are the factors that we can change for a gas. So in the first case, right, in the first situation, you can see mass and temperature are constant. So therefore, we are dealing with uh, pressure and volume. And in the second case, if it is pressure and temperature, then mass and volume are constant. And in the last one, volume and temperature, which means pressure and mass are going to be constant, right? So remember, these are the factors, the parameters that we can change for a gas, right? And yeah, so this is just a rough revision about these things. And about this H rho G thing, right? And also I need to mention this part, right? And also remember, if we are using different shapes of containers, right? It doesn't matter actually, right? We discussed about these things. So if this is the starting point and this is H1 height and this is H2. So this A, B, C, all these are given in the theory note, right? So this point will be having H1 rho G, and this point also same H1 rho G. This point also H1 rho G. If you consider this point, it will be H1 plus H rho H2 rho G. Same thing, H1 plus H2 rho G. Likewise, it will happen, which means the shape of the container does not matter for the pressure. So remember this point, at same level of the same liquid, the pressure is going to be equal to each other, right? Going to be equal to each other. So same theory will be used when we are dealing with the U-tubes as well, right? U-tubes as well. So U-tube is a glass equipment which is made like a which is made uh, in a shape of a letter U, right? Like this. So if we pour a liquid here, right? So just imagine this is my arm A, this is B, and we are pouring liquid from B, and eventually it will be having the same equal levels like this, same equal levels. The reason is, so these are open, right? These the upper places are open. So which means here you will be experiencing the atmospheric pressure. And here also you will be experiencing the atmospheric pressure. So this molecule and this molecule will be also experiencing the atmospheric pressure, right? Those two will be having the atmospheric pressure. So therefore, if we consider these two molecules, so they are at the same molecule, same liquid, and also in the same level, right? So if we consider this point to be A, this point to be B, so what has happened at same liquid and same level, right? So this is the most important part. Same liquid, it must be the same liquid and also must be in the same level, right? Same liquid, same level. So therefore we can say PA will be equal to PB. PA will be equal to PB. So PA will be atmospheric pressure. PB will be also atmospheric pressure. So that's why you are having this sort of a liquid levels. But just imagine, so now I am applying external pressure here, right? I'm going to connect it into a pump. So from here, there's an external pressure applied. So in the first case, the liquid levels were here, but now you are experiencing external pressure from here. Now what will happen? The liquid level will be pushed down, right? The liquid level will be pushed down, and here the liquid level will go up, right? So this is a normal scenario, right? So this liquid level will go up and this liquid level will go down, right? And now, so I'll say the external pressure is P, right? External pressure is P, and the atmospheric pressure AP, right? Atmospheric pressure AP. So this is our liquid level. Now it is like this. Now we need to calculate the height difference between the two bars, right? Two arms, height difference. So again, you are choosing two levels, 2 points. This is going to be point A for the liquid molecule A. This is going to be liquid molecule B, right? So these two are at the same level. See, these two are at the same level. Same level, same liquid, right? Same level, same liquid. So therefore, you can write both A and B are in the same liquid and same level, right? So therefore, I label this height difference to be simple h, right? So therefore, I can write pressure at A will be equal to pressure at B. Pressure at A equal to pressure at B, right? Pressure at A equal to pressure at B. Why? The reason is this. Both A and B are in the same liquid and the same level, right? So pressure at A. So you need to place your fingers and you need to come from the outside of the outside world, right? Outside world. So in the outside world, you have atmospheric pressure, right? Still atmospheric pressure, still atmospheric pressure. So up to this place, you are experiencing the atmospheric pressure. After that, what you have? After the atmospheric pressure, there's a, oh God, there's a liquid column. There was a liquid column, right? After the atmospheric pressure, there was a liquid column. So then, God, I need to draw the diagram once again. Right, quickly I'll draw the diagram. So it was connected to the pump like this. And the liquid levels were like this. And this is point A, this is point B. And here you are having the external pressure. And here you are having atmospheric pressure. So as I mentioned, pressure at A equals pressure at B, right? The reason, same liquid, same pressure. The same liquid, same level, therefore same pressure, right? So as I'm mentioning, so you need to start at a point and you need to come from the outside world, right? So here you are having the atmospheric pressure. So up to this place, you are experiencing the atmospheric pressure, right? Atmospheric pressure. And if I take this liquid difference H, right? This liquid difference H, now you can see that above point A, there's a liquid column as well, right? So the pressure generated by the liquid column, we can take it by H rho G, right? H rho G. So up to this place, it was just atmospheric pressure. And when it comes to this place, what will happen? It will be atmospheric pressure plus the H rho G. Atmospheric pressure plus the H rho G, right? And in the other side, so here you have just the extra pressure, extra pressure, extra pressure, extra pressure. So here you are having just the extra pressure, right? So if you need to calculate the H value, then extra pressure minus atmospheric pressure divided by rho G. This is the answer, right? Now tell me, did you understand that point? So normally, like there was only just one question from the YouTubes in the Edexcel papers, but in the theory classes, I gave you some questions related to pressure and all the stuff related to YouTubes, and even in your textbook, there's only just one simple calculation, right? Yeah. Okay, so I think you got this theory point, right? So please pay attention to those points. And there were so many good questions, and we discussed them in the classes as well. Those airplane and where you have the bottle in an airplane, and when it lands, what happens to the bottle? Likewise, there were so many good questions. So as I'm mentioning all the time, so if you have time, then please refer many questions as possible, and also refer the regional paper questions as well. Refer means like not to memorize or not to study them, just go through the question and uh, try to form your own answer, right? It doesn't matter whether you have written the answer or not. If you have already written the answer, just read it out. That's all, right? So that's all theory points. Those are the all theory points for these solids and liquid section. So next week we will be discussing. No, won't be any sessions tomorrow, but I will be needing 2 other days from next week. So it might be Monday and Tuesday, 27th and 28th, right? I will be uploading that, updating that in the WhatsApp community. So I will be needing 2 other days, 2 or 3 actually, right? We'll see. To in order to cover the next few sections. So the next ones are radioactivity, magnetism, and the astrophysics part. And also, I did not discuss about the energy related stuff, and also the momentum. And yeah, so we'll see, right? Those are some small small lessons. So we'll try to finish them within those 2 days. And that question was in the, I think, in a regional paper. I can't remember, but you can easily find that in the past paper question booklet where I gave the categorized one, right? So there was only like a simple question whether they are asking you to state the pressure and all the stuff. So just try to find it. As I can remember, you all got that correct, right? But the theory behind it is good. Okay, that's why I'm asking you to refer it. There was no calculation at all. They were just asking the numbers, like what is the pressure, what is the reason for this imploding thing, right? Likewise. And also, yeah, you might get questions from this HROG part related to a submarine or something like that, right? So those are the use case scenarios, right? So therefore, please pay attention to those points, and yeah, please study, okay? So I will be concluding the session for today, and hopefully next week I will be covering the next few sessions like astrophysics and magnetism and radioactivity within 2 days time. Okay. So thank you for joining. And as I am mentioning all the time, please utilize your time in the maximum effort. Okay. Okay. Thank you and have a nice day. Bye.